morning. The title of the presentation is UML State Chart Autocoding for the Mars Science Laboratory mission. The speaker is Benowitz from JPL.
Thank you. My name is Ed Benowitz. I've been with the Jet Propulsion Lab for about 10 years, and for the last 5 years or so, I've been writing flight software for the Mars Science Lab mission. Good news, it worked. The picture on the left shows you the size of it. The MSL rover is on the right side, and you can compare it to the size of some of the previous rovers, and also, the humans in there for scale. And the picture on the right is one of the first ones that came down, and it's one of my favorites because you can see the shadow in the self-portrait. So we were jumping for joy on landing night. So today's talk, I'm going to get into state chart autocoding, which is a tool I use to help me in my task of writing flight software. The basic idea is you automatically generate flight code from a state diagram. And the code that's generated using this has been flying on Curiosity since launch. It helped get us to Mars, and it's actually still running there every day when we boot up. So here's an overview of our process. Let's see, get my pointer out here. So we start with a drawing tool. In this case, we chose to use Magic Draw, and the developer draws a state chart diagram. And we wrote our own tool that takes the output of the drawing tool, happens to be an XML file. So this is our tool here, the autocoder. Our tool takes as input this state chart, and out pops source code that's actually compiled into the flight code. So I'll go over some pros and cons. The one advantage is that the code and the documentation are always in sync. For stuff that's not auto-coded, we found, okay, you do your design review, you make a state chart, and then you change the code. The diagrams don't typically get updated, and they may not always be precise. So in this case, you get much more precise and more detailed diagrams for your design reviews. The next thing is you're able to accommodate changes late in the game, and this is proven very true on MSL. We had great interaction with system engineers. They gave us inputs in the form of state diagrams, and there were, through the change process, the structure of the state charts needed a change, and it was very simple for me to go back and drag a few arrows here and there late in the game, click the button, regenerate the code, and add some support code. But that was much simpler than trying to reverse engineer code I'd written a year ago to create a state chart in my head and then try to modify it. So that was definitely a win. It also encouraged communication quite a bit. I can't hand system engineers a bunch of C code always, but I was able to hand them fairly detailed state charts, even more detailed than the input specifications they gave me, and that helped system engineers and testers really follow along with the flow of execution as the code was running in the test bed. So I think that was a win, especially for people who are coming up new and haven't been with the flight project throughout the cycle. It's very helpful for new testers who are coming up later in the game. It also forces you to consider off-nominal situations. This is kind of a win we didn't anticipate. But when you look at the generated code and you look at the state chart, it kind of forces you to think about, okay, if I get such and such event in such and such state, what do I do? If you just went and wrote the code and didn't think too much about the state chart, you might not even consider those sort of oddball off-nominal scenarios. So it was a good forcing function, and that was something I didn't anticipate, but it really helped me as a developer to consider off-nominal scenarios in a new way. Now, there are some drawbacks. People can draw state machines that are a chain, that are just one state and one event going to the next, so it looks like a very large linked list. And perhaps those linked lists could get as long as 20 states, 20 transitions with no loops. And in that case, I feel a state chart is not really the appropriate solution. And in fact, in those cases, I wrote my own little chunk of code to just walk through it. So a state chart is not always the right answer. I think you have to use the right tool for the right situation. And a little bit later, I'll talk about when I think it's appropriate and when it's not. And another con is, yes, the drawing actually does take some time. I honestly believe, though, that it's a good investment. And that in the end, given all the advantages, it actually saves me development time. And particularly writing some of the more tedious parts of the code. But yes, drawing a diagram does take time, and that is an upfront cost you pay. However, if you had to do a design review, you would typically be doing state chart drawing anyway, maybe not to this detailed level. But again, it's a forcing function. It forces you to be more precise, more detailed as you're going through your design review process. So, sure, on the right page. Okay. So here are some areas that we used it on in MSL. These are areas that I was responsible for. In the picture, you can see the cruise phase. So this is what the spacecraft looks like after it launches and is on the way to Mars. So we call that the cruise phase. And there's a whole area of attitude control that's done by very talented GNC engineers. So I can't take credit for that. But what I worked on with the state charts sits on top of the attitude control system. It's basically a series of high-level state machines that send the low-level attitude control commands to that area of software. So it's higher level. It's a series of state machines that are pretty large in size. We had 10 state charts to do this that were all intercommunicating with each other. Excuse me, about a total of 100 states altogether. And what this does is retries in off-nominal situations. If the ACS system had a failure, it could do retries. It could try perhaps a different piece of hardware. And all of this implemented very high-level commands, such as point the spacecraft somewhere else, attain a certain type of attitude knowledge, or perform a trajectory correction maneuver. So I was very excited when we actually did our correction maneuvers and could see, the output come down in telemetry. And this is an area where I think state charts are very applicable. The system engineers gave me their version of how they wanted it to work, but it wasn't quite precise enough to generate code. So what I ended up doing was redrawing their state charts in Magic Draw, and making events precise and conditions more precise, and handle things that really weren't of interest to system engineering, but were very important for flight software. And that's how we did it, and it worked. We're at Mars. Another area of use that I think is a good application is spacecraft modes. In the pictures, you can see the different configurations that MSL had. It was inside a launch vehicle during launch mode. You saw the picture already of cruise mode as it goes from Earth to Mars. Then there's another mode, the very exciting 10 minutes of terror for entry, descent, and landing as it's parachuting down and using the sky crane to go to the Martian through Mars. And then finally when it's landed in rover mode. So there's a lot of reconfigurations that need to happen along these phases, with the exception of the entry, descent, and landing, which they managed on their own. So I was responsible for getting the hardware in the right state and executing any actions that needed to happen as you change from one mode to another. It might be powering on and off devices or reconfiguring the telecom. So that's the gist of it. So even though the number of states that are visible to the system and to the operations manager is much smaller than the 50, 50 states is what it took to actually implement it. So there's kind of a level of abstraction where the system engineer only sees, on the order of, 10 or 20 states, but inside the actual implementation, there are quite a few more to make that happen. Okay, so now I'm going to get a little bit more into what the generated code looks like, how the generated code works. So there are several key concepts in the state machine world that we need to translate to flight code. So you have states, which I think you're all probably familiar with, and events, which is, something happens and that takes you from one state to another state. So that's what I'm calling an event. So the way we implement these, each event maps directly to a C function call. And we can attach additional arguments to an event. And we pass into every event function pointer to the state machine structure. Now this state itself is just represented as an enumeration. And inside the event function, there's a switch statement which takes in the state. So we're switching on an enum. And the way we chose to implement this, and this was sort of consistent with the coding guidelines that were established on MSL, where state machines are flattened, so that all you see in your enumeration of the states is the lowest level leaf on the tree of the state machine. So I'm going to walk you through an example here. Get out my pointer. So here's where we start. We enter into this idle state. This is all cooked up. Notice if you want to move from one state to another, you have to have an event. So we have this event. This is a junction. And depending on this value of this condition, we'll either go to state A or state B. So this is a function that I will write that tells you, returns a Boolean. And then depending on that, we can, if we're in state B, if we get event 2, come back to idle. If we're in state A and we get an event, we'll go back to idle. And note here we have a composite state, which is one state nested inside another. Okay, so that's our example state chart. And now we're going to look at the generated code for that particular state chart. So here is the enumeration containing all the states. And note that there are only the child states, the lowest level states are in the enumeration. The composite state goes away. Here we have a little structure that just stores the state enumeration, so that's all the data storage we have. And then for every event, we have a function here. So here's the prototypes in the header file, and we have a little constructor, a little initialization for our state machine to set the initial state. And we also have a little bit of error handling prototype, just in case the state somehow got set to a bogus value in flight. And this is how we deal with that. Okay, so this is the C code. Here's the initialization. It sets the initial state to idle, and it runs the entry function inside that state. Here's event 2. Again, here's the switch statement I was talking about. So if we're in idle, nothing happens. If we get event 2, well, we're in this child state, we go back to idle and we run the idle entry function. And similarly for here, state B, here's what happens. So you can kind of see how it works. You get an event, you figure out what state you're in, and you run the actions. And the other key thing to notice here, this is flattened. There's no hierarchy explicit in the code. All right, and here's the other event. So you remember we had a junction where we had to decide based on this Boolean valued function which state we're going to go into, either the child or state B. So here's how that plays out, different actions taken in each branch. And this is the error handling case where if the state happened to be in some invalid value, we would deal with it in this way. This is basically an assert saying this can never happen. So moving a step up in how you'd implement flight software, you notice in here there's no reference any synchronization mechanisms, no semaphore. So it was a very plain C. But in a real flight system, you're going to have probably multiple tasks, some synchronization method. So state charts are independent of that. On our project, we happen to use inter-process communication to do that. So you have a series of tasks sending messages to each other. And basically, here's how we handle that. Inside your message handler, when you receive an IPC message, you call one of these event functions, and that's how the state machine is informed. So outside of the state machine, there's queues, there's IPC, and this is all underneath it. So it's very independent of the synchronization mechanism that you choose to use for your project. This is a little overview of the internals of the autocoder. We have a front end which reads in an XML file. This is basically the XML file is the storage format used by the Magic Draw tool. So we could parse that all in, and we build up a little. This is written in Java, by the way. We build up a little model of the state machine, bunch of Java classes, and then we have separate Java classes that actually do the code generation. They basically walk through the state machine model. And we had several backends. And this has actually been successful in that we have different backends for different flight projects. The whole process sort of initiated on another mission, the sim mission. And what we did is we wrote a completely new backend that was compliant with the coding standards for the Mars rover. And that's, oops, pardon me. Let's see. There we go. That was compliant with the coding standards for the Mars rover, and that's what ended up flying it. So the benefits of this is you can be relatively independent of the coding standard. You can write a new backend. The other model, for example, didn't do the flattening operation, and it used a little bit different code generation. Just as a side note, the tools change over time. So I'll talk a little bit more about that later. But the front end, though, may have to change as your drawing tool changes over time. So that's something to be aware of. So here's some example features of state charts that we support, simple states. I've already shown you events with transition and guards. If you're not too familiar with this, with how the diagrams look, this says when I get an event, and this is a guard in the square brackets. So the event comes in, and if the guard says it's okay to run, then you perform this action. And then this code gets run when you enter the state. So we support all of those. Here's an example of an internal transition. So we're staying inside the state, and we got this event. We're not going out of it. And if the guard says it's okay, then we'll perform some action, but we won't change the state. We also support self loops, junctions, as you can see here, kind of like an if statement. As I said before, we support composite states, which is basically states within a state, and also orthogonal regions. These are two state machines within a state that can run in parallel. I'll talk a little bit more about that later, some restrictions on that. So we impose some of our own restrictions here to help us with the code generation. So we say that every transition has to be started by an event. Also, because the code itself that's generated doesn't have any synchronization embedded within it, we don't let you publish an event while you're handling another event. So basically the way around that is you send a message out on the inter-process communication layer, and that takes care of the synchronization for us. Also, we don't allow nested orthogonal regions. So the other thing is you can always draw a state chart that's quite ambiguous. So we kind of have a development guide that says, best practices that we'd recommend. So for a junction, for example, you want to only use them in this if-else form if you can. The reason is, right, just from the drawing, it's not always clear if you had a whole chain of if-then-elses, which conditions would execute first. So this avoids that ambiguity. Also, we kind of encourage people to stay away from orthogonal regions, especially if you send the same event to multiple orthogonal regions. It's not clear which region might handle the event first. So that's another gotcha. So we recommend staying away from that. And also, you can't have, let's say, my event along several transitions coming out of the same state in multiple directions. So each event only comes out of a state once. And these are all just to avoid ambiguity. Okay. Timers are part of the UML spec, but we chose not to implement that. So we just used good old C code to implement timers and create our own timeout event. That doesn't seem to have been a problem. All right, so some lessons learned having used this tool on a flight project all the way through. It was very useful in accommodating late-breaking changes, and they do happen. And they happened in this area on multiple occasions, so that was very useful. The state charts, not the code itself, but just the visual state charts were used outside of flight software. And system engineers and the test engineers were very happy to have this in their pocket. It was a great way to do communication and just for myself and the system engineers to resolve some ambiguities and to go through some detailed scenarios. It was very, very easy to walk through. The test engineers really appreciate this stuff. This is much more detailed than the state charts that systems gave me to work with. So that was very handy for them to actually walk through, in real time in a test session, to have a nice picture they could stick on their monitor and see where they were going and see what states they were. And also just for myself, I went through with a red marker for my unit testing, and I checked off every state and every transition. We also used code coverage tools, but as I was writing my own tests, it was nice to have a picture that I could actually walk through and keep track of where I was going. When you first start out and you have your first design, there's a temptation to say, well, I've only got 3 states. It's going to be real simple. I don't need a state chart. I'll just code it up by hand. And that may be the case. But what I found is the state machine grows over time. And when you just do the nominal situations in your state chart, it may be small. And then you start adding off nominal. And it's going to grow. So that was helpful in accommodating the late changes and the growth in off-nominal situations. As a style guide, I started off using orthogonal regions, and then I moved away from it. One, the state chart becomes visually too large to see what's going on if you try to merge too many state charts into one and have several orthogonal regions. But the other one is ambiguity. If you send the same event to a state chart, and it could potentially be handled by multiple orthogonal regions, who runs first? And so to get around that, I actually turned this event into 2 events, and I labeled them, and I sent them in different order. So I knew exactly which event would arrive in which order. But if you avoid orthogonal regions, you get rid of some of that ambiguity. The last one has pretty big practical consequences. I ended up using the same tool from start to finish of the project. I think I started on Magic Draw 12, and by the time the project finished, we were on version 17 or something like that. But I stuck with 12. It was fine. But in between all those changes, their file format changed significantly. So if I wanted to work with the newest version of the tool, I would have to go back to the front end and rejigger portions of it. The other warning is that UML stored in XML between tools is not going to be so compatible as you would hope. And that's a disappointment. They've been working on it for a number of years trying to get them more compatible, but my experience is they're not. And so that's something to watch out for. So I would say pick a tool that you're comfortable with and stick with it, or be ready to make changes to your front end as your tool is going to change over time, because the compatibility, unfortunately, is just not there. So I'm going to give you some more lessons learned on when to use a state chart and when not to. So my kind of rule of thumb is, if the state chart has branching or looping, that's a great candidate for using the state chart in the autocoding process. When your state chart looks like this, and that chain can go on for 20 states, not a real good situation to use a state chart in. It's just much simpler to write code that can run through this chain on your own. And drawing something like that's a big chain of 20 or so states with just a single link going through them, not a good use of time, I would say. Some autocoding techniques expect you to hand edit the generated code. This is not what we do. Once the autocode is generated, we do not touch it. And if you need to modify the auto-generated code, you make the changes in your diagram. So that's a rule I would encourage. Beyond this autocoder, if for anyone else generating code, hand editing them has caused problems for people in my project. So I would recommend getting your code generator into shape and generating acceptable code at all times. Now, getting project buy-in, having gone through this, getting the project's blessing on the generated code early is very important. And I would also recommend strictly following the project's coding guidelines, and that's what we did here. Here we were actually lucky enough to have a spec for what state charts should look like if they were manually generated. And that was a big, I'd say a great guide. And what we did is we generated code exactly matching that spec. So that made getting project buy-in much easier, because we generated code that they specifically asked for. If your project doesn't use state chart autocoders, but let's say your project uses state charts, if you don't specify what they're supposed to look like, what ends up happening is everyone comes up with their own way, and it's implemented very inconsistently. And I've seen that in multiple projects. So even shying away from autocoding, make a spec, tell people how you want them to implement their state codes, just for readability. So you can see what's going on. And that's kind of a plus of the autocoders, that it forces people to get code that looks, follows the guidelines. All right, so that's the show for me, and I'm happy to take questions. Thank you. Yes.
I think this is fascinating. So here's my question. How much time or effort do you think you saved going through the autocoding process? Or did you?
So unfortunately, I don't have numbers that measure how much time I saved. I can say that these late-breaking changes in the project would have caused me to go back and have to figure out what states were there in the first place. And so having it there at the end was a win. I can tell you how long it took to physically draw the state charts. There is a certain ramp-up curve. So as you're first drawing it, it takes some while to get used to the drawing tools. But I had previous experience on another project, and so the time it actually took me to draw the state charts was not too bad. I mean, one chart you can crank out in a day and get it compiling and running. So that, I don't think once you get up that initial curve, I don't think the drawing time is too bad. But I think for maintenance especially, it helps. It helps to have the diagram there with you too, not just for how fast can you type the code, right? It's not how fast can I type it, it's how well can you understand it.
I think what I mentioned, just to repeat the question for the video recording, if we could do that, we don't necessarily always pick up
Okay. Sorry. The first question was, how much time did I save? Okay. Sure, yes.
Yeah, a couple questions. One, so there is an XML standard that the tool is trying to meet? Is that approved?
Funny thing about standards, there's so many of them. Yes, there is. There's a standard for the structure of the state chart. Unfortunately, that one particular structure does not include how does the drawing look, how is the drawing laid out. So that at one point was quite vendor dependent. Now they're trying to come out with a spec for the drawing layout, but from what I've read, that's been very unsuccessful, and still large incompatibility problems. The other thing is, even though there's a spec, the spec changes. So, as you go from a pre-UML2 to a UML2, well, yes, there's a spec for both of them, but they've changed. So now your tool has to change. So that's going to be a frustration that we've had and probably will continue for some time, unfortunately. Yes.
And I had a different question. So did you need any data from, the state charts all operate on function based, so you don't need any data input? Did you need symbols of data into the magic draw? Did I make that clear?
Yes. Sorry. So the question was, do I need to import any data? What I type is C function calls. So I need to generate prototypes for those function calls by hand and implement them by hand. The only times I needed to add anything significant to the model was when events have arguments attached to them. So I want to stick it integer. I kind of hacked that into the model, but again, it was just typing in code directly the declaration of that data type. So that was really the only place where I needed to sort of inject some data. But everything in the charts is basically direct C call. So, yes, in the back. A little bit, not too well.
I got two questions for you. One of them, have you investigated using cost tools, i.e. specifically MATLAB, Simulink, or for example, the Artisan or some kind of knowledge-oriented tools? And the second question is the code that you, and if you did that, what was the feedback from system engineering and software engineering?
Right. Okay. Oh, go ahead. Sorry.
Let me finish this. Like, the second question is, when you produced that code, was it real-time worthy? And was it
What was that?
real-time worthy?
Real-time worthy?
Yeah, can you put it in a real-time system? And can you put it in a space system?
Yeah. Okay. So there were a couple of questions. First one was, have we considered generating code using the commercial tools? And the second one was, is it real-time worthy? To answer the second one very quickly, yes, it's real-time worthy. It's on Mars right now. Yes, no problems there. The first question about using the vendor's code generation, that's an experiment that's been done in the past. There are papers out on the Deep Space One mission and on the Deep Impact mission where they used Stateflow, I believe, from MATLAB to do this. And what they had to do was they took the generated code and they had to post-process it to make it flight-like. So there was the general feeling that it was a bunch of work to get the code into a format that was deemed acceptable by the flight software team, and a lot of it was code parsing and then regeneration. So the advantage of this approach is, we're in control of the tool, and we have a model of the state chart, so it's easier for us to generate code from a state chart model than it is from trying to parse code and then reformat it. So that's been the feeling is, we need the control. We want to use our own data structures in a particular way in a particular project's coding format. And so that was the reason we went and wrote our own. And even project to project, they wanted different code to pop out. And so having that was handy for us. Yeah. Okay. Yes.
How far along was the autocoder when you started? And can you talk a little bit about the level of effort it took to fine tune it for MSL?
Sure. Question was, how far along was the autocoder before I started, and how much fine tuning did we have to do? The autocoder had been developed under several research projects before and were used on a previous mission. So the front end and the middle end were all very stable. I rewrote the back end in, let's see, it was probably about a month total to get the whole back end written and tested. So that was the level of effort. There were a few minor tweaks here and there at the very beginning of MSL. But the remarkable thing that, during the course of the 5-year mission, or 5-year development effort, or so that I was on the project, it was remarkably stable. We basically did not touch the autocoder after a few months into the project, which was not the case for other tools we use. So I'm very happy with that once we got it up and running. You don't want to have to be changing your tools all the time as you're developing. So it was very stable. Joe.
Eddie, 2 questions. Were you the only developer who used the tool? Or if not, how many people on the MSL team ended up using it? And secondly, how did it impact your unit testing? Did you auto-code any of your unit test framework, or was that still done by hand?
Okay, so the question is, who else used it besides me, and how did it impact my testing? So at the start of the project, there were 2 people using it, and one of them left the project. So now there was 1. So that's just me. So yes, there's a bias in this that I wrote it, and I'm also the only user. So yes, that's true. I can say that we're on other projects. The line management has been much more supportive, and in fact, it's the same tool is now being used by 5 or 6 developers. So that's good. Now, about the unit testing, I tested the generated code exactly like other flight software. So our unit test, we use gcov for code coverage, and that confirmed that, yes, I went through every line of generated code, I hit it with my unit tests, and that's how we went about doing the test. So it wasn't really any different from any other flight software test effort in that respect. It was treated as any other flight code with the same amount of rigor. Yeah. Yes?
Excuse me. UML defines a bunch of other design diagrams. I prefer state rendition diagrams over other, but in your case, when you guys were preparing these autocoders, were you looking at other diagrams as well, or it was primarily focused on state rendition diagrams?
So in our, the question was, have I looked at other diagrams besides state charts? So in our typical design process, the main ones we focus on are actually activity diagrams, let's see, with the swim lanes, and state charts. I personally feel that the state chart is the one to do the coding with. A lot of the activity diagrams are dealing with multiple modules sending messages to each other back and forth. And this generates code within a single module. So I would shy away from doing that, but other people are looking into that on other research tasks. Yeah.
Thank you.
Are we out of time? Okay. Thank you.